July 1st, 2025. What should have been a routine overnight scan at NASA's Atlas telescope instead triggered an instant system-wide alarm. At 4.5 billion kilometers out, astronomers spotted what appeared to be an interstellar comet, later named 3Atlas, hurtling toward the Sun at 58 kilometers per second, its orbital path utterly unlike anything seen this decade. Within hours, international networks scrambled to confirm the hyperbolic trajectory, but as data poured in, whispers of shape-shifting anomalies and bizarre physical traits flooded scientific channels. If the world's best telescopes barely recognized what they'd found, how could anyone predict what these anomalies mean for our understanding of the universe? This is What Are the Shape-Shifting Anomalies Orbiting 3I/Atlas, NASA's unprecedented 2025 alert, and the reality behind the headlines may be stranger than fiction. At 2:13 a.m. Chilean time, the Atlas night crew was halfway through their scheduled sequence when the alert window snapped open. A11 just a string of letters and numbers flashed on the monitor, tagged by the automated system for an orbit that didn't fit any known pattern. Quinlan Brown, the junior operator, was first to spot the flag. Within seconds, Larry Deno and John Tonry were awake and logged into the Slack channel, their phones buzzing on silent in the observatory's control room. The Slack feed filled with clipped messages. Check the astrometry. Is this real? Hyperbolic? Calibration routines started running again. The team pulled up the original exposures, pixel by pixel, hunting for any sign of a software glitch or cosmic ray hit that could have spoofed the detection. The object was faint, just above the noise, but the track was clean, slicing through the starfield at a steep angle. At 4.5 astronomical units from the Sun, it was farther out than Jupiter, moving at a pace that left no doubt. This was no ordinary comet. Tonry called for a second telescope to verify the coordinates. Brown double-checked the Minor Planet Center portal, entering the preliminary orbit data. The system's response was immediate. Possible interstellar origin. The room shifted from routine to electric. Deno's voice cut through the chatter. If this holds, we're looking at a third interstellar. The alert protocol triggered a cascade of emails and pings to partner observatories. Each minute counted. The crew re-ran the detection pipeline, swapped in archival images, and pushed for confirmation. For a handful of tense hours, the world's best surveyors watched as a new cosmic visitor, flagged by a handful of pixels and a string of code, upended the night's quiet routine. The Minor Planet Center in Cambridge, Massachusetts, received the first Atlas alert just before dawn. Within minutes, their analysts opened the pipeline to cross-check the object's motion against thousands of archived survey points. MPECJ-07 was issued at 0618 UTC, listing the preliminary orbit and inviting urgent follow-up from observatories worldwide. By midday, telescopes in Arizona, Hawaii, and South Africa had submitted fresh astrometric data, each set confirming the object's position and speed. The numbers told a consistent story. The orbit was hyperbolic, with a velocity exceeding 58 kilometers per second relative to the Sun. No solar system comet moves this fast. Yaoling Chen, an amateur astronomer in Taiwan, was one of the first outside the professional network to spot the anomaly. She pulled up ZTF images from mid-June and posted her findings to an astronomy forum. There's something off about this track. Has anyone else checked? Her careful measurements extended the observation arc by 2 weeks, tightening orbital calculations and ruling out a bound origin. As the data poured in, the MPC issued 4 more bulletins, J08, J09, J10, J11, each incorporating new positions, refining the trajectory, and updating the world's comet trackers. By the time the 5th circular was published, 31 observatories had contributed 122 observations. The orbit solution was now robust. Analysts at JPL and ESA ran independent models, all converging on the same result. The object was not only unbound, but its inbound vector pointed far beyond the plane of the ecliptic, with no plausible source among known solar system reservoirs. With the interstellar status locked in, the focus turned to the comet's physical properties and the question of what secrets it might carry from another star system. Orbit modelers at JPL and ESA watched the numbers settle into place over a tense 48 hours. The solution was clear: 3I/A/T LAS would sweep through the inner solar system on a hyperbolic path, but never cross into Earth's neighborhood. Its closest approach to the Sun, perihelion, lands on October 30, 2025, at a distance of 1.36 astronomical units. That puts it just inside Mars' orbit, still more than 200 million kilometers from the Sun. The minimum distance to Earth comes weeks later, on December 19th, 2025. Even then, the comet will be 1.8 astronomical units away, about 270 million kilometers, or more than 700 times farther than the Moon. This is well beyond the orbit of Mars, a safe margin by any standard. The orbital solution has been checked and rechecked, with over 4,000 astrometric measurements from ground and space telescopes feeding the models. The margin of error is less than 500,000 kilometers, nowhere near enough to change the outcome. Dynamical specialists point to the comet's extraordinary speed, nearly 58 kilometers per second as it barrels through the solar system. No gravitational nudge from any planet can pull it off course. Its trajectory is so steep that even the most extreme scenarios yield a missed distance far outside any potential hazard zone. For planetary defense teams, 3I/A/TLAS is a visitor, not a threat. The focus remains on tracking its arc, mapping every subtle curve as it threads between Mars and Earth's orbits, and preparing for the brief window when its physical properties will be most accessible. The question now turns to the comet's makeup. What secrets might its surface and gases reveal as it swings around the Sun and heads back into interstellar space? Dynamicists at JPL and ESA began their work with a puzzle. How do you weigh a visitor from another star system, sighted as a faint streak of light tens of millions of kilometers away? The answer rests in numbers, thousands of astrometric measurements, each one a pinprick on the sky, charting the comet's progress night after night. Over 4,000 data points from ground telescopes and space observatories formed the backbone of the mass and dynamics analysis. The first task was to estimate the size of 3I/Atlas's nucleus. Photometric readings, corrected for distance and phase angle, pointed to a body between 0.32 and 5.6 kilometers across. Most models converged on a diameter less than 1 kilometer, but the range stayed wide, a reminder of how little direct detail could be seen at such a distance. The real breakthrough came from tracking the comet's subtle deviations from a perfect, gravity-driven path. Every outburst of gas or dust, every jet of material, nudged the nucleus ever so slightly. These tiny accelerations, called non-gravitational accelerations, became the key. By measuring the rate at which the comet's trajectory shifted, and pairing that with estimates of gas outflow velocity and mass loss rates drawn from JWST's infrared maps and Hubble's imaging, dynamicists could set a lower bound on the comet's mass. The calculation is simple in principle. The force of escaping gas must be balanced by the inertia of the nucleus. If the comet were too light, its path would veer sharply every time a jet fired. If it were too heavy, the jets would barely register. For 3I/Atlas, the numbers settled around 3.3 times 10 to the 10th power kilograms, more than 33 billion tons. That's a mass towering over most known comets, and even at the smallest plausible size, it implies an object with remarkable density or strength. Rotation added another layer. Light curve analysis revealed a rotation period of 16.79 hours. That's slow for a comet this size, hinting at a sturdy, perhaps monolithic core rather than a loose rubble pile. The stability of its spin, even as outgassing activity ramped up, surprised many. Models predicted that strong jets should have spun up or slowed down the nucleus by now. But 3I/Atlas held its pace. Momentum balance modeling, the backbone of these estimates, required careful attention to every assumption. The geometry of jets, the beaming factor of outflowing gas, the dust-to-gas ratio, and the velocity of escaping molecules. Adjust any one of these, and the mass estimate shifts. Yet across all plausible scenarios, the conclusion remained: this comet is massive, with a nucleus that resists the forces trying to tear it apart. Each new observation sharpened the picture, but the core result stood firm. A compact, hefty traveler shaped by forces far from our own solar cradle. Spectroscopy teams around the world logged in as soon as the comet's trajectory was confirmed. At NASA Goddard, chemists and postdocs gathered in the control room, eyes fixed on the first spectral data streaming in from the IRTF and Gemini telescopes. The initial readings were puzzling. The coma's infrared signature hinted at a volatile mix, but the usual markers were faint or missing. Analysts expected to see water vapor, always the dominant ice in solar system comets. But the numbers didn't add up. Instead, the strongest absorption bands pointed to carbon dioxide, with water lagging far behind. Lab groups in Maryland and Göttingen, Tin-Jian, spent hours rechecking calibration, convinced the instrument was misreading the blend. Yet each new spectrum confirmed the same result. The coma was saturated with carbon dioxide, a ratio that, if accurate, would be unprecedented. The search for cyanogen, a staple in cometary chemistry, brought more uncertainty. Observers at the VLT in Chile scoured the optical and near UV bands for the telltale CN emission, but the line stayed buried in noise. Some hinted at faint traces, others saw nothing at all. The debate spilled into Slack channels and late-night video calls, with chemists trading hypotheses about hidden reservoirs or unfamiliar molecular pathways. No consensus formed, but the absence of strong CN emission only deepened the mystery. Metal lines offered another puzzle. Spectroscopists scanned for atomic nickel, a rare but known component in comet tails, and compared it to the expected iron signature. Early data suggested a possible nickel presence, but iron remained elusive. This imbalance challenged every existing model of comet formation. In solar system bodies, iron and nickel typically travel together, forged in the same stellar environments. Here, the familiar pattern broke down. Was this a quirk of detection limits or evidence of a different planetary nursery? By late July, the chemistry teams had filled whiteboards with possible scenarios. Some proposed a crust of exotic ices. Others argued for a deep mantle of carbon-rich dust. All agreed on one point. 3I/A TLAS was unlike any comet they had studied. The rush to secure more spectra intensified, with every major observatory scrambling for a clear night. Each new observation fed the sense of wonder and the growing realization that the comet's chemistry might rewrite the textbook on interstellar matter. At 11:17 p.m. UTC, a post appeared on r/space with a blurry J/E WST image and a headline that read, "Is 3I/ATLAS changing shape in real time?" The user, AstroHunter77, claimed to have spotted a shifting outline in the comet's coma, a faint bulge that seemed to move between exposures. Within hours, the thread exploded. Comments poured in from amateur astronomers and self-styled skywatchers, each adding screenshots, hand-drawn overlays, or wild speculation. One reply, by Space Mystic, stitched together a GIF showing subtle flickers in the dust cloud. The caption, "Natural or engineered? You tell me." The meme spread fast. X, TikTok, and Discord channels lit up with short clips and looping animations, each more dramatic than the last. Hashtags like #ShapeshifterComet and #AlienAtlas trended for 2 days straight. Influencer accounts with hundreds of thousands of followers reposted the original GIF, tagging NASA and demanding answers. Some even claimed the object's brightness was pulsing in code. The speculation snowballed. Is this a probe? Is NASA hiding something? Science YouTubers jumped in. Some ran frame-by-frame breakdowns of the JWST images, highlighting every pixel that seemed to shift. Others built elaborate theories from the comet's changing light curve, mixing technical jargon with clickbait. The most viral video racked up over 2 million views in a weekend. In chat rooms and comment threads, the story grew legs. Every new image, every minor update in the comet's appearance was seized on as proof of something extraordinary. Beneath the noise, a few voices tried to slow things down. Experienced amateur astronomers pointed to the effects of solar wind, outgassing, and the limitations of infrared imaging. But the rumor had already outpaced the facts. By the end of the week, the phrase shape-shifting anomaly was everywhere, an internet echo, born from a handful of ambiguous pixels and amplified by the hunger for cosmic mystery. NASA's public affairs team responded within hours of the first viral posts. They issued a statement through the official FAQ, addressing the so-called shape-shifting claims head-on. All current observations remain fully consistent with natural cometary behavior. The so-called shape-shifting events are visual artifacts of dust emission and nucleus spin. ESA reinforced the message, publishing a detailed explainer on their website. Spokespersons pointed to decades of comet imaging, where jets of gas and sunlight routinely sculpt shifting halos and tails. The agency's social channels hosted AMA sessions with comet physicists who walked viewers through the science of outgassing, nucleus rotation, and the tricks of infrared imaging. For every meme or speculative video, there was a direct scientific answer, always grounded in the available data. While the rumor mill spun, mission planners faced a different reality. The idea of launching a rapid response CubeSat to intercept 3/ATLAS never moved beyond the discussion stage. Both NASA and ESA confirmed in their September briefings that no mission was planned or canceled. The comet's speed, over 58 kilometers per second, and outbound trajectory made any intercept unfeasible. Instead, every available telescope, from JWST to ground-based arrays, was tasked with remote observation. The focus shifted to maximizing data during the brief window the comet would be visible. Researchers coordinated observation schedules, pooled resources, and prepared to adapt to weather and equipment setbacks. The lesson was clear. When a true interstellar visitor appears, the window for in-depth study is narrow and unforgiving. Astrophysicists turned their attention to the deeper question: where did 3/ATLAS come from? Stellar dynamicists ran simulations tracing its path backward, testing models for ejection from the Carina-Columba group, or perhaps a close encounter with an M-dwarf star. The data offered no consensus. Some models favored a violent birth in a dense cluster. Others pointed to a quieter origin in a protoplanetary disk. The only certainty was uncertainty. Each new interstellar object has rewritten the rules, expanding the catalog of what's possible in planet formation and cosmic migration. The comet's passage leaves the field with more questions than answers. A reminder that in science, mystery is not a flaw, but an invitation. On July 4, 2025, the Atlas telescope in Chile detected 31I/Atlas at 4.5 astronomical units from the Sun, marking only the third confirmed interstellar object ever observed. Within weeks, over 4,000 astrometric measurements from observatories worldwide established its hyperbolic orbit, confirming it would pass safely at 1.8 astronomical units from Earth on December 19, 2025. Spectroscopic analysis revealed an unusual 8:1 ratio of carbon dioxide to water and the presence of cyanide, raising questions about its origin and the diversity of planetary systems. Despite viral claims of shape-shifting anomalies, no peer-reviewed data supports such interpretations. As noted in official Minor Planet Center bulletins and NASA statements, the true composition and ejection history of 3/Atlas remain open scientific questions. Its brief passage reminds us that each interstellar visitor challenges current models and expands our understanding of the galaxy, evidence that the solar system is just one crossroads in a much larger cosmic journey.